Black holes are formed when the remnants of a supernova collapse under their own gravity, creating an area where gravity is so strong that not even light can escape. These enigmatic objects continue to intrigue scientists and challenge our understanding of physics. After a supernova explosion, the remaining debris, known as supernova remnants, scatters throughout space. These remnants enrich the interstellar medium with heavy elements, which are crucial for the formation of new stars and planetary systems. Stars play a vital role in the cosmic ecosystem by producing the elements necessary for life. Their life cycles contribute to the continuous recycling of matter in the universe, driving the evolution of galaxies and the formation of new stars. Astronomers use a variety of techniques to observe and study stars at different stages of their life cycles. By analyzing light spectra and using telescopes, they gather data that helps us understand the complex processes governing stellar evolution. Astronomers use advanced telescopes and satellites to study stars at different stages of their life cycles. By analyzing light spectra, they gather information on a star's composition, temperature, and distance, offering insights into stellar evolution. Notable examples of stars in various stages include Betelgeuse, a red supergiant nearing its end, and the Crab Nebula, a supernova remnant. Observing these celestial objects helps scientists understand the dynamic processes governing stellar lifetimes. Theoretical models are essential for predicting star behavior and evolution. These models use complex mathematical equations to simulate conditions within stars, providing valuable predictions about their future states and enhancing our knowledge of cosmic phenomena. Our Sun, currently a main-sequence star, will eventually expand into a red giant before shedding its outer layers to become a white dwarf. This future transformation is a natural part of a star's life cycle. As we contemplate the future of our Sun, it's fascinating to realize that one day it will expand into a red giant, engulfing nearby planets before shedding its outer layers and leaving behind a white dwarf. In certain cases, if the remaining core is sufficiently massive, it can collapse further to form a black hole. These enigmatic objects have gravitational pulls so strong that even light cannot escape their grasp. What remains after a supernova explosion are supernova remnants, which are clouds of gas and dust. These remnants are crucial for enriching the universe with heavy elements, dispersing them across the cosmos. Supernovae play an essential role in the cosmos, not only by dispersing elements, but also by triggering new star formation. The shock waves from these explosions compress nearby gas clouds, initiating the birth of new stars. This continuous cycle of star birth, life, death, and rebirth ensures the universe remains dynamic and ever-changing. Old stars die, their remnants contribute to the creation of new stars, and thus the cosmic cycle perpetuates itself endlessly. Astrophysicists and astronomers dedicate their careers to studying these celestial phenomena. Through advanced telescopes and space missions, they gather invaluable data, furthering our understanding of the universe and uncovering the mysteries behind the life cycle of stars. From the birth in nebulae to the explosive deaths in supernovae, the life cycle of a star is a testament to the universe's complexity and beauty. Each stage offers unique insights into the forces that shape our cosmos. The life cycle of a star is essential to understand because it illuminates the processes that shape galaxies. By studying star formation and death, we gain insights into the origins of elements and the forces driving cosmic evolution. Stars form in giant molecular clouds called nebulas. These vast, cold regions of space contain dense concentrations of gas and dust. Over time, certain conditions trigger the collapse of these clouds, leading to star formation. Gravity plays a crucial role in this process by pulling gas and dust together. As the material clumps, it forms a dense core that continues to attract more matter. This gravitational collapse is the first step in a star's birth. A protostar is the early stage in a star's life, characterized by a contracting core surrounded by a vast envelope of gas. During this phase, the core begins to heat up, setting the stage for nuclear fusion. As the protostar accumulates more mass, the pressure and temperature in its core rise. Eventually, these conditions become extreme enough to ignite nuclear fusion. Hydrogen atoms begin fusing into helium, releasing tremendous energy. Once nuclear fusion ignites, the protostar evolves into a main sequence star. In this phase, it achieves a stable state, fusing hydrogen into helium in its core. Main sequence stars spend most of their lifetimes here. A star's mass is crucial in determining its lifespan and ultimate fate. Massive stars burn through their nuclear fuel quickly and live shorter, more dramatic lives. Smaller stars have longer, more stable lifespans. Stars produce energy through nuclear fusion, converting hydrogen into helium in their cores. This process releases vast amounts of energy, providing the light and heat we observe. Fusion powers stars and sustains their luminosity throughout their lifetimes. As a star exhausts its hydrogen fuel, it transforms into a red giant, expanding immensely and cooling on the surface. This dramatic change marks a crucial phase in its evolution, significantly altering its appearance and behavior. With the core contracting, helium fusion begins, producing heavier elements like carbon and oxygen. This process releases immense energy, causing the star to pulsate and shed its outer layers, further contributing to its red giant status. Low-mass stars eventually expel their outer layers, creating beautiful planetary nebulas. These glowing shells of gas and dust illustrate the star's final breath, leaving behind a fascinating and intricate structure visible across vast distances. The remnant core of a low-mass star becomes a white dwarf, a dense, Earth-sized stellar object. Without fuel for fusion, it gradually cools and fades, emitting residual heat and light over billions of years. White dwarfs slowly cool, transitioning from hot, bright objects to dim, cold remnants. This cooling process takes billions of years, during which the white dwarf remains a silent witness to the end stages of stellar evolution. High-mass stars evolve into supergiants as they exhaust their hydrogen fuel. Their outer layers expand dramatically, shining brightly with a reddish hue. This stage signifies the star's progression towards the end of its life cycle. As the supergiant's core contracts, it undergoes a process known as core collapse. Gravity overwhelms the thermal pressure, causing the core to shrink rapidly. This sets the stage for a cataclysmic event. A supernova explosion occurs when the core collapses, releasing an immense amount of energy. This explosion can outshine entire galaxies momentarily and disperses stellar material into space, enriching the cosmic environment with new elements. The powerful shock waves from supernova explosions can trigger the formation of star clusters and stellar nurseries. These regions become fertile grounds for new stars to form, continuing the cycle of birth and death in the cosmos. Summarizing the life cycle of a star, we journey from a nebula to a protostar, through the main sequence, and finally to a red giant or supernova. Each phase reveals the intricacies of stellar evolution. Explore the wonders of the universe by delving deeper into the mysteries of stars. Subscribe to our channel for more captivating cosmic content and join us on this endless journey through the stars.